First of all, I'd like to thank Enrique for this invitation. Yeah, I'm happy. I was here 2 years ago. I think it's the exact same room. So it's a great pleasure to be back here. Looks like today we have a SJTU invasion of Erlangen. All right, so today I will share with you some work I did in the last few years in the direction of interacting particle system for both classical and quantum systems. So this is what I try to cover. First, talk about the random batch methods for classical interacting particle systems. So the joint work with a lady, also my young colleague, and Jiao Liu at Duke University. Then one particular application, which I think is important, is in molecular dynamics. Okay. And then I will move on to talk about quantum embodied problems and quantum Monte Carlo. So basically the problem I try to solve is very fundamental equations that everybody knows, F equals ma, all right? So it's Newton's second law. So it takes the form of a system of ODEs. So here we have a bunch of m particles with positions xi for the ith particle, positions xi, and vi is velocity, all right? So the dots here is just time derivative. So the first line is the definition, right? dx dt equals velocity. And second line is f equals ma. So here assume all the particles are exact same. So m mass says is 1. So the left-hand side is clearly acceleration. Okay, the derivative, time derivative velocity is a acceleration. And the right-hand side is just f. So here f comes from interacting of particles. So particles, they have force acted upon each other. All right, what's important is the summation term. So each particle interact with all the other particles. Okay, so here essentially we have a m-1 summations. Okay, so this is usually called second order interacting particle systems, where phi is the potential. All right, so minus negative gradient. A negative gradient of potential is just force. Right? So it's force between the particles. Okay. Sometimes you take so-called overdamped limit, you get a first order system. All right, you eliminate the velocity, for example, in certain asymptotic regimes. Then you have this sort of Langevin equation, interacting particle Langevin equations. You still have this interacting particles potential force k. K is interacting force. We normalize it, divided by m-1. And here, V is the external potential. You have some external force. Okay, you get an external potential. You may also assume this noisy background, right? So B is the Brownian motion. Okay. So these are the systems we try to solve. Talking about applications, it's everywhere. Okay, if you have a long enough career, there's a big probability you'll solve this equation. Okay. So here I just list a few. Well, in physics and chemistry, molecular dynamics, for example. In astrophysics, where you have a gravitational force between stars, galaxies. All right. In biology, in the last 2 decades, people use so-called agent-based models. So you model interaction between different biological agents. Okay. And social science, economics, where interact. I mean, the people they trade, for example. That's kind of interaction between different economic agents. All right. Also, the particle method is also a numerical method to solve usually high-dimensional PDEs. All right, it's called the Lagrangian methods versus Eulerian, which solve PDEs. So here you solve PDEs by particle method. Usually, for example, in kinetic equations, the mean field equations, very high-dimensional PDE. So difficult here actually is the size of the problem. So here notice that we have a summation, big summation. Okay. And the number of particles usually is astronomical. For example, in cosmology, astrophysics, n can be as high as 10 to the 20. All right. In plasma, it's also 10 to the 20. The numerical particle methods, the largest computation you can do is 10 to the 9 to 10 to the 12. There are many other applications. Okay. So the difficulty here is that we have to add a lot of terms. Okay, so it's really the size of the problem. It's not that we don't know how to solve ODEs. Everybody here knows how to solve ODEs, right? But the problem is that this summation. Okay, so you see all the n summation for each I. But you have n of them, so it's odd n square. Complexity odd n square, right? That's the difficulty here. Okay. And n square usually is forbidden, sort of forbidden for classical computation. And there are very famous algorithms developed to address this issue, for example, fast Fourier transform. Okay. And also, particularly for the problem I'm going to talk about, fast multiple methods introduced by Rocklin and Greengard. Those are two of the so-called top 10 algorithms of last century. Okay. So it's about how they reduce odd n squared to odd n or n log n. So today I will show you a method we introduced. It's called a random batch methods. All right. So the goal is to reduce from n squared, computation comes from n squared to odd n. And actually it's a very simple method and also very general. It works for all force, different force, all different potential. Okay. So that's the joint work with Lei Li and Jianguo Liu. It's actually embarrassingly simple. Okay. Only 2 steps. I hope everybody can understand. You can go back to program. I'm sure you can finish programming in half an hour. Well, last time I was in Changchun, East Normal University. There were 2 young faculty who saw the advertisement of my talk. And then during my talk, when I said 30 minutes, said that's an overstatement. It took them 15 minutes to program it. Okay. Anyway, so it's very simple. 2 steps. So the first step, we do so-called random shuffling. So you have totally capital M particles. You divide them into small groups, okay, but randomly. You divide the total n particles into little n groups. Each group has little p particles, where p times little n equals capital N. All right? The key is here that p, the size of each group has to be very small compared to capital N. It can be as small as 2. It means basically 2 particles each group. You just do a random reshuffling. Like if you play a deck of cards or mahjong games in China, after each game you do random reshuffling and reorder, right? Regroup, put into different groups. Then at each time step, each particle only interact with particle in the same group, same small group. You forget other particles. You just interact among your own group, between your own group. That's it, okay? That's it. Well, if you write an algorithm, okay, well, if you're smart, you're probably smarter than the people that I talk about, maybe 10 minutes. Just few lines. You pick up time step, tau is small, okay? Assume that you have done m steps, so next step, what do? You partition the capital M particle randomly, okay, has to be a particular random partition into little n groups. And then in this dynamic system, the summation term, instead of adding all the terms, capital M minus 1, you add p minus 1 term. So for each I, you only pick up those j in the same group as I. Then you add and average. Okay, that's it. Okay, that's it. Well, apparently the cost is now order n, because now the summation, instead of capital M minus 1 term, is p minus 1, or p is like order 1, okay? N can be astronomical, but p is order 1, a few hundred, whatever. So it's essentially order 1 summation here for each particle. So for n particle is order n, right? And also this random shuffling, that of course you have to pay some price. And of course already in the 70s there are already order n algorithm to do this random shuffling. For example, if you use MATLAB, you just use this subroutine called it's a random permutation, you just call that subroutine. That's why it's only 10 minutes program, okay? Even for grad student. Well, there's another version, okay? Instead of doing the random partition, for each step I just randomly grab p particles and let them interact. Then you put it back. It's like you have basketball X. You randomly draw X and let them interact and put it back. All right, then you randomly draw another p particles and let them interact, put it back. After little n steps, because little n times p is capital N. After little n times you finish 1 time step. Then you repeat, okay? Well, this is little bit different than the other version, because now at each time step, Some particles may be picked more than once, and some particles may be missed, okay? But as you accumulate in time, it's almost the same, okay, very similar. So both algorithms can be implemented, very easily. Of course, you may wonder, well, I have been being very lazy, right? I only do part of the job. I didn't finish the work. So at each time, I saved effort by order n. Does it take n times longer to finish the job? Okay? Or intuitively, if you only do part of the job, you take a longer time, okay, n times longer to finish. If that's the case, then you didn't save anything, okay? But here, what's important is that I'm going to prove that actually the time step can be independent of capital N. That's the key. I save all the n effort for each time step, but it does not take n times longer to finish the job. It sounds too good to be true. I'm telling you a way to be lazy, you can get away from it, okay? Don't do that in your work research, but this is the way, this is how you can cheat and you get away from it. Of course, this idea, crazy idea, there's some inspired by some other ideas. For example, here you have strong group in machine learning. We know if you do a deeper neural network, at the end of the day, you have to solve a global minimization problem for a high-dimensional non-convex functions, all right? So there, of course, the most popular algorithm is stochastic gradient descent method. Right? Everybody knows. So you have a loss function which has many terms. At each gradient descent step, you just randomly pick up a mini batch, okay? And then you do the gradient descent. Of course, number one, you save the effort. Number two, if it's random, so you add some noise. This noise will give you some escape probability to get out of the local minimum. So give you some probability to get to the global minimum, right? So that's a popular method. If you come from Boltzmann community, and the most popular method to solve Boltzmann is so-called direct simulation Monte Carlo, where you randomly pick up two particles, let them collide, and of course there's some conservation law you have to satisfy. All right, it's called Nambu's algorithm or the Babilov, whatever. Of course, there physically just two particle interaction, but in our method it's n particle interaction, but I probably randomly pick up a few. Okay, it's a little bit different, but it's very similar. Okay, now I'm going to tell you I have been being lazy, but I get away from it. Okay, I'm going to prove theorem that it works. So to prove theorem, I have to make some assumptions, all right? Assume some regularities. For example, this external potential, V, I assume is strongly convex, which means that V minus x squared is still convex. Okay, here I have constant R here. It's more convex than R over 2 times x squared, or some bounded derivative. You can allow derivative to be grow, but polynomially. And now the interacting force, K, assumed to be bounded, all right? Lipschitz with Lipschitz constant L and bounded second derivative. So here I assume this convexity coefficient R is bigger than 2 times this Lipschitz constant L, all right? So actually you can prove, well, if I don't have the noise term, okay, it's just the interacting particle, then you can prove actually the L2 distance. If you start with two different initial data, then you have two solutions, xi and yi. The L2 distance time derivative is bounded by itself times this constant minus R minus 2L. So under this condition, R bigger than 2L, then this coefficient is negative, which means that it's contracted. This dynamics is contracted, all right? So L2 distance actually decay exponentially to 0. Of course, this is boring. If you add the noise, the sigma is the strength of noise. If you add the noise, actually, the invariant measure or global equilibrium actually can be a Gibbs measure. It's not trivial, it's Gibbs measure or Maxwellian and so on. Anyway, so that's the condition. So now assume the analytic solution is xi and random batch solution is xi tilde. Of course, error is the difference between the two, right? And it's a vector. So I take a L2 norm and put the expected value because it's a random method. So, okay, expected value. You can also measure the error by so-called Wasserman 2 distance. So here we have a stochastic differential equations, all right? So here you have a probability distribution of for each x and xi tilde, it's mu and nu. And so you take this definition wasn't distance, all right? So here the capital pi, pi is the joint distribution of the two random particles, all right? So actually these two errors are basically equivalent, okay? If you can prove one, you get the other. So this is a little theorem, okay? So now assume those as set conditions on V and K are satisfied, then the error, all right, is bounded by essentially square root of tau, where tau is time step. So it's half the order in time step. Why half the order? Actually, what we have is actually the Monte Carlo method in time. Well, you probably know Monte Carlo method. If you have n sample, capital N samples, the error of Monte Carlo sampling is 1 over square root of n, so it's half the order in samples. Here, actually, we have Monte Carlo method in time. So the error is square root of time step, okay? It's sort of, Monte Carlo time. But that's not very important. What's important is this constant C. You can prove under the condition that I stated, the C is independent of capital N. So what does that mean? It means, so for example, if I want the error to be like 10 to the minus 3, I just have to select the time step to 10 to the minus 6. Even my N can be 10 to the zillion, doesn't matter, okay? So now you see, my time step is independent of N, which means indeed I not need N times longer to finish the work. So I cheated and I succeeded, okay, right? So that's the L2 error, and you get similar error for the Waston-2 distance between the empirical measure of the two system, all right? Also square root of C, square root of tau. So that's the key, time step is independent of capital N. You wonder why this can happen, why this is true. Actually, you compute the error, we committed error, right? So before you have this n term summation, n minus 1, the average. Now I just take p minus 1 terms, okay? So that's the truncation error, right? The truncation error actually is order 1. Okay, I'm not doing the right job, it's order 1, clearly. However, if you take expected value, you assume, okay, this is the chi is the error. If you assume fixed x, expected value of the chi is 0. So in average, I'm doing the right thing, okay? So instead of taking total average, I take a partial average, random partial average. Then the expected value, expected error is 0. But this is very easy to understand. I mean, today, every day, I mean, there's a lot of news about Donald Trump. Before the US election, there are a lot of polls. Did you follow, right? Usually they have a lot of polls. They poll maybe, they don't poll all the voters because that's too many. Usually it's more than 130 million, whatever. You don't call everyone. You just poll small samples, maybe 1,000. You get average. Okay, maybe Trump is 52%, Harris 48%. There's some errors usually, okay, margin of error, but it's small. So you see, you just take a random partial sum, partial average. Then you have a pretty good prediction of who is going to win. Okay. But of course, it must be unbiased. You cannot just pull Texas is a red state. Most people will vote for Republicans, okay, Trump. If it's California, it's blue, right? Usually they go for Democrats. You cannot do that. You have to close your eye, have a uniform, unbiased. Then it works, okay? It works. So it's not only the philosophy of life, math is philosophy for your life. Okay? You can take a partial random average. Well, later we have some more sophisticated analysis. For example, second order systems. We can even allow disparate species and weights. All right, not all the particles are the same. Also for a long time, people were wondering, when you have error, especially Monte Carlo error, the error will accumulate in time. Eventually, of course, you get garbage. Right? But you can prove, actually, joint work with Zhen Nanzhou. Now he's at Westlake University, and he's still in a year, a brilliant student. So actually, we can prove on the same contraction in a long time, the error is still square root of tau, independent of t. okay, as long as it's contracted. You have the causivity or hypercausivity. So in the long time, it's still accurate. Also, I want to talk about error of the random batch, okay. You have to still have to discretize ODE, Olama, Riyama, whatever, use some skill discretization. Even for fully time discrete random batch, Chen Nan, his student also proved that you still get a similar error, okay. You can also analyze the mean field limit. If you basically define empirical measure, basically put the direct mass at each particle, all right? And of course, when n go to infinity, you get the mean field limit. That's actually a Fock-Planck equation. So this drift term comes from external potential, and the interacting part give you this convolution, where k is the interacting force, all right? Then the noise Brownian motion give you this diffusion term. So actually, this method is not only an efficient method to solve the original particle system, you can also view this as this particle method to solve the mean field Fock-Planck equation. Okay, so this is the original particle mu n, and this is the random batch particle systems. Of course, when time step go to 0, it converges. This is the mean field Fock-Planck equation, which is valid when n is very large. So this random batch method can be viewed as a numerical particle method to solve the Fock-Planck equation. Okay, and you can, the error, if you do analysis, is the summation of a random batch error plus the mean field error. The mean field error is usually 1 over square root of n. So you see, if n is large, this is not only a good method to solve the particle system, it's also a good method to solve the mean field equation. Then, of course, when we prove theorem, we have to make assumptions on the regularities, nice functions, smooth functions. But practically, actually, this method works for even for singular potential. So here we actually have a bunch of examples. For example, if you this Dyson Brownian motion, it's basically you want to find the eigenvalues of a random matrix, right? So you can solve that, find that eigenvalue by solving interacting particle systems. Here, lambda j is the jth eigenvalue of this random matrix. All right, so this is interacting particle system. You have external force for linear potential essentially. Now the interacting force actually can be singular because it's the difference, 1 over difference between different eigenvalues. If two eigenvalues are close or multiple eigenvalues, I mean, this is a singular potential, right? This second example is a charge. This is a very famous physical problem. It's called the Thomson problem, where you put like n electrons on the unit sphere, and they are subject to Coulomb interaction, all right? You ask, what is the equilibrium distribution? Okay. So that's called the Thomson problem. Actually have semicircle laws. So here again, you solve interacting particles with a Coulomb force. Here F is Coulomb, which is singular actually. It's 1 over distance between particles. Okay. And this is the Brownian motion on sphere. This PS, the projection operator to projection onto the unit sphere. And this is some crazy finance model where actually it's a very long-range interaction. Here, the force increasing distance is not a physical, okay? And also you have a multiplicative noise here. The strength of noise depends on solution. So all this example works numerically. Although the proof theorem is difficult, but it works. Well, after our work, there has been several extensions. For example, in machine learning, people are interested in sampling of a general distribution. One way to do it is use Stein variational gradient descent. You can write it as interacting Langevin equation. So this group at Duke, Jianfeng Liu and Jianguo Liu and so on. You can also use this to compute like Gibbs measures that generate by interacting particle systems with singular potential, for example, Lena-Jones potential, okay? Actually, Enrique has done some very interesting work for like control of synchronization. Where you have synchronization, you can describe synchronization by particle method, a particle system. Okay. For example, Kuramoto model, which actually Kuramoto got the Boltzmann medal this year for his work for this model, a synchronization model. So Enrique did a beautiful work on control of this using random batch. And with Song Yiha at the Seoul National University, we also wrote a few papers on agent-based models for collective behavior, like swarming, flockings, like Cook-Smell models, Wissig models, also Kuramoto models, and so on. But next, actually, I will mainly focus on important physical examples is molecular dynamics. All right. So it's joint work with Zhenli Xu is also my colleague in the math department. So here we are interested in solving Coulomb interaction, okay, which has many important applications. For example, AF drug discoveries, AF for new materials, okay. So here, this is the Coulomb force. I mean, actually, in molecular dynamics, there are a lot. It's very complicated. You have terms corresponding to bonds, angles, torsions. You have a Lennard-Jones potential, which actually is very singular, all right. And then you have Coulomb interaction. That's the most challenging part. Because the Coulomb interaction here, the Qi, Qj are the charges, all right. Then the numerator, the denominator is actually the distance between particle I and j. Rij is distance between two electrons, all right. So clearly, this is all the n squared summation. So the idea is based on so-called E-word splitting. So about 100 years ago, E-word has this beautiful, simple but beautiful idea. So here is a long-range interaction because the force decays in 1 over r. So it's very slow decaying, all right? So if you want to throw away large r has to be very large, okay, to maintain small r. But you would just write 1 over r into 1 of the air function. You know, air function is from 0 to x of e to the minus x squared, okay, over 2. Air function divided by r, and this is a 1 minus air function. So that's the identity, right? And actually, the air function is near r is air function divided by r is smooth near r equals 0, okay? So it's a removable singularity, r equals 0. So it's actually a smooth function. So for smooth function, you can take a Fourier transform. Well, 1 minus air function, complementary air function, divided by r actually decay exponentially in r. So effectively, because it decay exponentially, effectively it's a short-range interaction. I'm going to throw away r when r is relatively large because it decay exponentially. So therefore, for this exponential decay term, I just add as it is. I truncate r for suitably large r. It's like short-range interaction, like summation. There's few term summation. However, the smooth part I put in the Fourier space, and then you have this e to the minus k squared term, all right? And that's like Gaussian. It's like Gaussian distribution. If it's Gaussian, here you have to add all the k's, infinite number of k's. Because it's Gaussian, so now I'm going to do, instead of adding all the k's, I'm going to do a random batch. I just select randomly a few k's. I'm not going to add all the k's. So the cost will be reduced from all the n squared to all the n. Another important thing is here, because this e to the minus k is a Gaussian sampling, Gaussian distribution, you know how to sample Gaussians, right? So you just sample the Gaussian offline. Beforehand, you take a sample, take a lot of sample from Gaussian, you save it in the library. Then at each random batch step, you just pick up a few p term from the sampling. This corresponds to important sampling, okay? You know, in Monte Carlo method, not only have to get average right, you have to reduce the variance, because according to central limit theorem, the error comes from the variance. You have to find a way to reduce error variance. One way to effectively reduce the variance is important sampling. So by sample, pre-sample e to the minus the Gaussian, actually we are implement a random Monte Carlo method with important sampling, which allow us to compute for a long time with a very good accuracy, okay? So it's a random batch plus important sampling. So here is we just pick up p term summations, okay? We sample it a priori. You put in some library, then each time you just take a few terms, few samples. So for example, if you we did a numeric simulation of charge inversion in a salty environment where we have odd atom simulation of like 17,000 water molecules. So if you compare the CPU time, actually, if you do original E-word, it's like 16,000. Random batch E-word, that's what we call it, with P equals 100. So here we totally have 17,000 particles, but each random batch will only pick up 100 particles, okay? So the time is like one order of magnitude smaller, all right? And if you compare the cost, original E-word is this line here, while our case in the end, particles is actually linear. So yeah, we compare P equals 10 and 100. The complexity is linear in N. And later, another colleague of mine, Hong Liang, who is a biophysicist, he learned our method, and he's a biologist, so he ran a big simulation. So he just exhausted the SJTU's supercomputer with like 10,000 CPUs. So he did the simulation of 10,000 molecules. All right. Of course, the computer efficiency is one order of magnitude faster. What's more amazing is the scalability. All right. It turns out if you do the state-of-the-art molecular dynamics simulation, for example, particle mesh method is called PPPM, or particle mesh E-word PME. Those are the state-of-art molecular dynamics simulator that's being used for drug discovery, new materials. Those methods are all based on FFT. And we know FFT is not scalable, okay? It's non-local. But this random batch method is scalable. You look at the parallel efficiency. With 10,000 CPUs, the PPPM has like 20% parallelability. While the random batch here, we take 50, each batch is 50 or 100 particles. The parallelability is almost 100. It's almost 100 parallel. The reason is when you have to do parallel computing, the message passing, you have to pass the message from one CPU to the others, called message passing. That will eat up most of the cost. So the saving you have for each single CPUs by random batch is completely wiped out by the cost of message passing, all right? But with the random batch method, each time you only involve a few particle interactions. So you only involve message passing among very few CPUs. So that significantly reduces the message passing cost, which allow us to maintain a parallelability almost 100%. So it's completely scalable, highly scalable. Well, of course, you did all the tests, all right? You did the 1 million time step from femtosecond to nanosecond. And it maintained a very good accuracy compared with PPPM. With the particles, each random batch is like a few hundred. I'm talking about 10 to the 7 molecular dynamics simulation. Each random batch is 10 to the 2, okay? You see that they did all the standard benchmark comparisons for accuracies. And these are actually for hydrodynamic variables, like kinetic energy. Also, you get nice agreement. And later, actually, molecular dynamics are very sophisticated. They're all different ensembles. This MVE, MPT, all these different ensembles. So this method has been extended to all these different ensembles. Okay. And more recently, actually, we also use random batch not only for the long-range interaction, we also use it for short-range interaction. Okay. And now, actually, with one GPU, we can do 10 million all-atom molecular dynamics simulation, only in one GPU. So that's our recent result. So with that, actually, I have an AI institute in Chongqing. It's beautiful. Chongqing is a very fascinating city. You should visit. Okay. It's as fascinating as Shanghai, by the way. So we have actually open source random batch simulator. You can, it's in GitHub. If you are interested, you just, here's the address. And if you want to do a test, you just email this address. And actually, we collaborate with a high-performance computer company in China, Shugang. And now we build our software, this random batch software, with 10 to 7 atom molecular dynamics in one GPU. Here it is. So all you need is just have this equipment on your desktop. You can do molecular dynamics with 10 to 7 particles. Before, people can only do 10 to 6 million scales. Now, 10 million in your office. Okay, you don't need a massive parallel computer. One GPU with this machine. Why this is very exciting all of a sudden? I'm very excited. I mean, now, there are a lot of big news about AI for science. The biggest, of course, is the AlphaFold, which they got a Nobel Prize last year, right? With AlphaFold, actually, you can now predict very accurately the structural proteins, maybe all proteins on Earth, okay, from its sequence. There was a joke. I mean, there's some very famous Chinese scientists, biologists, who actually before used this what is called I forgot the English. 冷冻电镜. Anyway, I mean, they use this very expensive equipment. What you know the English? What's the English for this 冷冻电镜? I forgot. Anyway, so they used to do experiment. All right. Before, in old days, you need one PhD thesis to find the protein one structure one protein. Now, of course, AlphaFold did them all. So this experimentalist, people were joking you're going to be out of a job, right? So the Yanning actually is a household name in China in this business. So people are joking, okay, you have no job to do. So this is what she said in blogs. She likes to write blogs. She's internet sensation. Okay. She was in prison, now she came back to China in Shenzhen, actually. Had a big research institute. This is what she wrote. Of course, she said it's great thing, AlphaFold and protein. But she said, well, compared with the contribution to protein folding, I hope that AI can help more molecular dynamic simulation for structural biology. This field is in urgent need to progress. Okay. But that's exactly what we did, right? You have a very fast molecular dynamic simulation technology, which is a very important part for if you want to drug design. Okay. You have to do this free energy perturbation, where you need to do a lot of molecular dynamic simulation. Also for new material designs. So I think it's a very important part in AI for science, where you have to do a lot of simulation for F equals ma. All right, any questions so far?
Can I ask a question? So the number of particles is capital N.
Yes,
right?
yeah.
And you take batches of size P.
P, yeah.
So what is there an optimal choice?
Yeah, that's a good question. Well, the smaller P, of course, is more efficient, but it increases the variance. Actually, we have you can compute the variance. Variance is proportional to 1 over square root P minus 1. So increase P will reduce the variance. So it's a balance between efficiency and error, of course. Well, for this molecular dynamic simulation, usually we pick P to be like 10 to the 2, while capital N can be 10 to the 7. So that usually is good enough. But we don't have a good accuracy analysis for cooling interaction because it's very single, it's difficult. But for smooth interaction, we have this error estimate. Yeah. This,
computational cost, how does it go with P? Of course, when P is bigger, what?
Yeah, sure. We usually take P to the 10 to the 2, so it's like 10 times faster. Yeah. This question back there. Yeah.
How many molecules is needed for?
Well, okay, if you want to do drug design, the candidate molecules 10 to the 60. Okay. But with AI, you can easily identify maybe very quickly instead of 10 to 60, maybe a few hundred possible molecules with probability to make the drugs you want. So this AI-aided drug design can accelerate before pre-clinical trial stage, before it takes years. Now it just takes a few months. Okay. Yeah.
Thanks for this part of the talk. That's very nice. One question related to what you mentioned that usually you take like P particles randomly.
Yeah.
There is not a way to fix like the batches. I mean, I can imagine that if your computational kernel is local, then it doesn't make too much sense to pick less.
Sure. This works for long range. Yeah. Short range, of course, is easy, right?
Yeah. And therefore, it doesn't make sense
That's a good question. I mean, we don't have exactly, it's a kind of empirical, right? We just picked, 100, 500. They're very similar. Of course, how do you sample? That's tricky business. Here in molecular dynamics, we have important sampling according to the Gaussian. But for other force kernel, you might have specific way to sample instead of a uniform distribution. If you have, for example, if you look, Lennard-Jones potential, which is very singular near the origin, we split this kernel into the smooth part, where we use random batch, and the singular part where we treat it like a short range interaction. Yeah. So you play some tricks for specific potential. Yeah.
And maybe last question, you mentioned that there were like applications to PDEs, but these PDEs are basically like meaningful limits of interaction.
High dimensional PDEs.
Right.
Where you have to use particle method, yes.
And besides, I don't know, a general PDE can be applied there?
Yeah, one example, we use this for Landau equation. I mean, that's kind of Boltzmann, but for plasma with Gleason limit, with Jose Correa at Oxford, actually. This collision term, collision is like summation, right? And it describes the summation, so we actually use it there, which can reduce the efficiency significantly because multiple integral, yes.
Basically, every time that you have a summation.
Yeah, every time you have a summation, remember from now on, okay, I tell you how to cheat, successfully cheat, okay. Every time you see big summations, average, you just do a partial summation, it always works.
Did you try for the fractional, these fractional diffusion operators are very popular, there is a lot of literature.
Yeah, that's why you have integral representation of it. I never tried it. I mean, I think most time when you have one usually works for deceptive systems. Does not work for like an oscillatory system. Okay, if you have oscillations usually you need a very high resolution. And this dissipation kills oscillations. That's not good. But as long as it's a dissipative system, then usually it works. So that's my experience.
Fractional diffusion operator.
Yeah. Even it's fractional diffusion, I expect it to work, although I never worked on it. The reason I didn't work it is because there are too many works on that. I don't want to jump into. I usually don't want to jump into a busy field. So, yeah, I think it's probably work, but we never. We should probably could try it. Yeah, thanks. Okay, now let me get to the quantum part. Okay, so I was talking about classical particle system, but now the first system. So it's this is joint work with two distinguished French mathematicians, François Gauss, École Polytechnique, and Theory Paul at the Sorbonne University. So here we have an M-body Schrödinger equation, which is the ultimate physical equation you want to solve. Okay, maybe now let's go and talk about quantum computing. That's designed for this equation. But anyway, so the M-body Schrödinger equation. The difficult here is, of course, curse of dimensionality, because here you have M particles. Each particle has three dimensions. So it's a PD of dimension 3n. Usually n is a few hundred. Okay. Of course, here the Hamiltonian has two parts. This kinetic part is basically Laplacian for each particles. All right. Then you have this Coulomb interaction between particles. This, of course, is so-called first principle simulation because there's no free parameters. Okay, if you can solve it, you understand everything about the physical world. You can design all kinds of jokes you need, for example. So here, of course, this interaction part, we can easily use random batch. So we have so-called random batch Schrödinger, where instead of add all the terms, basically, we just add one term. For each particle I, we randomly pick another particle j. Okay, so this summation, we get rid of summation. That's called a random batch. Of course, this is a theoretical result. We don't have a computer to solve this equation. Okay, we cannot use this for practical purpose, but maybe in the future. But for now, we have theory. So the theory says the following. And of course, for theory, you have to use von Neumann equation, which is basically an equation for density matrix. So here are Rn's density matrix, where this bracket is just commutator, all right, of these operators. So then we have a random batch von Neumann equation. So this is what we prove. We have to make some assumption on the potential, right? Symmetry and decay. Essentially what we find is that this WH is the Wigner transform, okay? And N1 is first marginal. So of course here we have to take first marginal. It does not work for wave function. it works for first marginal. The tilde is a random batch first marginal, you have to expect a value, all right? So difference between the random batch first marginal, it's a Wigner transform, and the original analytic solution. Well, this is a dual norm. Okay, explain that the dual norm. All right. It's bounded by some constant independent of n, number one, also independent of h bar, because h bar can be very small. It's a very stiff problem. It's highly oscillatory. Okay. So the error is linear. It's weak norm, so linear first order time step, and all the constant are independent of n, independent of h bar. It's a uniform error. So here, this is the definition of dual norm. Basically, you have a f minus m norm, essentially multiplied by essentially cm function. Okay, that's the dual norm. So it shows that it also works for quantum n-body problem. Okay, except that of course, we don't have a numeric simulation to show it works because it's something for the future. Okay, it's a theory for the future. Then with Xiantao Li and Penn State, actually we also extend this idea to so-called quantum Monte Carlo. So that said, you cannot afford to solve n-body Schrodinger equation, but people usually do in quantum chemistry is to find the ground state, which is the minimum eigenvalue of the Hamiltonian, quantum Hamiltonian. Okay. So there are different ways to do it. One way is to use Markov-Chain Monte Carlo. Okay. Hastings-Metropolis algorithm, for example. You can also solve this equation by solving interacting particle Langevin equation. Okay. So here are i's particles. So you have external potential, which is log of phi. Then you have this Coulomb interaction. Then you have some white noise. You have a white noise term. Okay. So the equilibrium solution of this dynamic system gives the distribution of the ground state. Okay. It's called a variation of Monte Carlo method. So here, of course, now, whenever you see summation, I just pick up a randomly one term. So for particle I just pick a random j, and then j of have the integral with I. Okay. So you see now I have this algorithm without the summation term. Basically, I pick p equals 2. Okay. The random batch has just 2 particles. And so you move like 400 Markov chains for 1,000 steps. If you just do Metropolis, the CPU time is like 1,500. If you solve this Langevin equation directly using Ola Maruyama, it's about 460, while with the random batch, it's only 50 units. This more general version for quantum Monte Carlo is called diffusive Monte Carlo. So here, instead of solving Schrodinger equation that has an I here before ddt, you just delete the I. It becomes Hit equation. The reason is Hit equation converges because they simply converge to equilibrium solution much faster. Okay, Schrodinger equation is conservative. So you can also solve this by some Langevin equation, all right? So this is a force term. You have external force, you have Coulomb interaction. And actually in the implementation, there are terms. You not only have binary interaction, you have a triple interaction. You have summation with 3 indices. But doesn't matter. This not only works for 2-body interaction, it works for any body interaction. Here, with summation of 3 indices, you just pick a random triplets, I, J, K. Okay? Then you delete the summation. So actually, you can carry the original. If you do direct diffusive Monte Carlo, it's quadratic in n, but now in our case, it's linear in n. Okay. And actually, so Aiton Telemo and Jose Carrillo, they also with Nicola Bellomo, yeah. So he's editor-chief of M3AS. So they edited this book series for active particles. So they invite me and Lei Li to write a review article for random batch. So I'm sorry, this is some Chinese. So it's extension to molecular dynamics, quantum Monte Carlo, many-body Schrodinger equation, social and biological collective behavior, sampling problem in statistics and machine learning, all right? So these are the applications. This work also was selected, every year SJTU select top 10 advancing science technology. So this work also was in one of the years. And also last year was, we got the first class Shanghai Natural Science Prize for this work. Okay, so here's the conclusion. So basically, you probably agree with me that Newton's equation and Schrödinger equation are two most fundamental equations in physics. Okay. So when you have m particles, computational cost is very expensive. So for both, we introduced this random batch method to reduce the cost from order n squared to order n. Very simple. The method is very simple. Compared to fast multiple, this is extremely simple. And theoretically, for classical particle, we can prove estimate, okay, independent of n. All right. For quantum dynamics, quantum mode, actually we can prove error, and that's for first marginal with error independent of n and also h bar. So it works all the way into semi-classical regime. Okay. And then we use it for classical molecular dynamics based on random batch E-word, and also quantum Monte Carlo. The cost is order n, and more important, it's highly scalable. Okay, it's highly parallel algorithms. Of course, there are a lot of theory and practice you can along the way. For example, can you prove estimate with a less regularity? So here we assume a nicer regularity to get a theorem, but you have Coulomb, for example, and those. And also for application, for quantum Monte Carlo, we can only do bosonic system. We don't know how to do a fermionic system. Because for fermionic system, this density function is not symmetric. If you switch two particles, you get a minus sign. Okay? So you have to use a Slater determinant. And we don't know how to do that random batch for this kind of setting. But most exciting applications we are currently doing, China is a leader of new energy vehicles and new energy batteries. All right? So this company, CATL, is the leading company for batteries, new energy batteries. So currently, we're working with them to do molecular dynamics for lithium battery design. Okay, so last week, actually, some colleagues were visiting them. So they're very interested in using this for the future new energy battery design. Okay, so with that, I stop. Thank you.